A 2-ton family sedan that hits 60 miles an hour in under 2 seconds. Not a track-only hypercar. Not a $1 million limited edition. A car you can order online and have delivered to your driveway. The secret isn't hiding in the battery pack or the software. It's spinning inside a motor smaller than a bowling ball, wrapped in a material borrowed from fighter jets and Formula One race cars. And the strangest part of the story is that Tesla told everyone exactly how it works, and almost nobody outside the engineering world noticed. When Tesla delivered the first Model S Plaid units in the summer of 2021, most of the attention went to the numbers. 0 to 60 in under 2 seconds. A top speed north of 200 miles per hour. A carbon fiber wheel design borrowed straight from motorsport. But during that delivery event, Elon Musk spent a few minutes talking about something far less flashy on the surface: the rotor inside the car's motor. He called it, in his words, arguably the most advanced motor on Earth outside of a laboratory. That's a bold claim from a man known for bold claims. But this time, the engineering behind it holds up. To understand why this matters, you need to understand what a rotor actually does. Inside an electric motor, the rotor is the spinning component that turns electrical energy into the mechanical force that pushes your car forward. For decades, rotors in most motors have relied on metal construction, usually held together with high-strength steel. That approach works, but it has a ceiling. Spin a metal rotor fast enough, and centrifugal force starts pulling it apart from the inside. Engineers have to build in safety margins, which means motors can only spin so fast before the risk of the whole thing flying apart becomes real. Tesla's answer was to wrap the copper rotor in a sleeve of carbon fiber, wound under extremely high tension. Musk explained on social media around the Plaid's launch that the carbon sleeve does two things. First, it creates a stronger electromagnetic field than a rotor held together purely by metal. Second, and just as important, it stops the copper rotor from expanding outward as it spins faster, which lets the whole assembly safely reach higher revolutions per minute than a conventional design could handle. According to Tesla, this was the first time a production electric motor had ever used a carbon overwrap rotor. Not a prototype. Not a concept car. A vehicle you could actually buy. Here's the part that made engineers pay attention. Carbon fiber and copper expand at very different rates when they heat up. That mismatch sounds like a minor technical footnote, but it's actually the whole reason nobody had done this before. If the carbon sleeve is wound too loosely, the rotor can loosen and destabilize once things heat up during hard driving. If it's wound too tight, the pressure can damage the copper underneath. Tesla's solution was to wind the fiber over the rotor at an extremely high tension load, so that the carbon actively compresses the copper and keeps it locked in place no matter how the temperature shifts. Musk put it simply: the carbon sleeve has to keep the copper rotor in compression, or it loosens at low temperatures because of that differential thermal expansion. Solving that problem on paper is one thing. Building a machine that can reliably do it thousands of times a day on a production line is a completely different challenge. And this is where the story gets genuinely interesting, because Tesla didn't have a machine capable of doing this when they started. One didn't exist anywhere in the world. So the company had to design and build it from scratch. That work fell largely to Tesla Automation, a manufacturing engineering group based in Prüm, Germany, that Tesla acquired years earlier when it was still known as Grauman Engineering. That team had to figure out how to wind carbon fiber around a spinning copper core at exactly the right tension, consistently, at scale, without a single existing blueprint to work from. That manufacturing achievement is arguably the more impressive story than the motor itself. Plenty of companies can sketch out a clever design on a whiteboard. Very few can turn that design into something that rolls off an assembly line by the thousands, every single one built to the same exacting tolerance. Tesla's carbon-wrapped rotor isn't protected purely by secrecy. Tesla actually filed a patent for the design, titled Permanent Magnet Motor with Wrapping, which became public in late 2021. In other words, the blueprint for the rotor itself isn't hidden. What's hard to copy isn't the concept. It's the production process, the tooling, and the manufacturing discipline needed to execute it consistently, which is a much steeper mountain to climb than reading a patent filing. It's worth pausing here to separate hype from substance, because there's plenty of hype around Tesla, and skepticism is healthy. Independent motor engineers have pointed out that some of the marketing language thrown around this motor, phrases like revolutionary or the most advanced motor in the world, oversimplifies what's actually a well-executed but incremental engineering solution to a known problem. Carbon fiber overwraps aren't a new material innovation. Aerospace and motorsport have used similar wrapping techniques for years. What Tesla did wasn't invent a new material property. It was solve the manufacturing puzzle of applying that known technique to a mass-produced electric motor rotor and do it profitably at scale. That's still a genuine achievement. It's just a narrower one than some headlines suggested at the time. So why does this matter beyond bragging rights for a fast sedan? Because the benefits of a carbon-wrapped rotor go well past straight-line acceleration. A stronger electromagnetic field from the same size motor means more power without needing to make the motor bulkier or heavier. And because the carbon sleeve is lighter than the steel bracing it replaces, the whole rotor assembly weighs less, which means less energy is needed to spin it in the first place. Less energy spent just moving the motor's own components translates into better efficiency, which for an everyday EV owner shows up as more range on the same battery pack rather than a spec sheet number that only matters at the drag strip. There's also a durability angle that doesn't get nearly as much attention as the 0 to 60 numbers. Metal components that heat up unevenly during hard use can develop subtle imbalances over time, the kind of wear that eventually shows up as vibration, reduced efficiency, or mechanical fatigue. A carbon sleeve, properly tensioned, helps keep that rotor geometrically stable across a wider range of operating temperatures. That's less exciting to talk about in a video, but it's the kind of engineering detail that actually matters over the years a person owns the car. None of this happened in a vacuum. Tesla's willingness to take manufacturing risks traces back to the company's earliest days. When Martin Eberhard and Mark Tarpenning founded Tesla in 2003, the idea of a genuinely fast, genuinely desirable electric car was treated as a novelty at best by most of the auto industry. Elon Musk joined as an investor and chairman in 2004 and pushed the company toward a different goal entirely: build electric vehicles that could beat gasoline cars on performance, not just on environmental credentials. The 2008 Roadster, built on a Lotus chassis, was the first real proof that this was possible. The Model S followed in 2012, then the Model X, then the Model 3 and Model Y, each one pulling Tesla further from a niche curiosity toward a mainstream automaker. The carbon-sleeved rotor motor in the Plaid is best understood as the latest chapter in that same pattern. Take a hard manufacturing problem nobody else has solved at scale, and solve it anyway. That pattern is now putting real pressure on the rest of the industry, even if the response has been uneven. Lucid Motors has arguably come closest to matching Tesla on raw engineering, with the Air Grand Touring performance offering genuinely excellent range and drivetrain efficiency. But Lucid produces vehicles in far smaller numbers, aimed mostly at a luxury buyer, without anywhere near Tesla's manufacturing scale. Rivian has carved out real demand for electric trucks and SUVs, backed by Amazon, but its motor technology has stayed closer to conventional designs rather than chasing this specific kind of rotor innovation. Traditional automakers like Ford and General Motors have made visible progress too, the F-150 Lightning and GM's Ultium platform among them, but both companies are still splitting resources between combustion vehicles and electric ones, which limits how aggressively either can chase next-generation motor technology. And globally, BYD has actually overtaken Tesla in total EV sales, leaning on a vertically integrated supply chain that keeps costs remarkably low, even as it continues working to build the same brand recognition in Western markets that Tesla already has. What that leaves is a fragmented competitive picture rather than a single company closing in on Tesla from one direction. Lucid has the engineering chops but not the scale. BYD has the scale but not yet the brand equity everywhere Tesla sells. Legacy automakers have brand trust built over decades but are still catching up on the base technology. Tesla, for now, is one of the few companies with a credible claim to all three: engineering depth, manufacturing scale, and brand recognition, working together at once. That said, it would be a mistake to treat this motor as some kind of guarantee of permanent dominance, and any honest account of Tesla's position has to include the real headwinds the company is facing. The carbon-wrapped motor is currently reserved for Tesla's performance trims, which cost significantly more than the company's mass-market vehicles. Whether this manufacturing process becomes affordable enough to reach cheaper trims like the standard Model 3 or Model Y remains an open question, and Tesla hasn't made firm public commitments either way. Meanwhile, the company has dealt with tightening profit margins, layoffs, and intense price competition from Chinese manufacturers like BYD, SAIC, and NIO, all of which can build vehicles at lower cost. That competition is a useful reminder that superior engineering on its own doesn't automatically translate into market dominance. Pricing, brand trust, charging infrastructure, and overall product strategy matter just as much as what's happening inside the motor housing. There's also the matter of how closely Tesla's public image is tied to Elon Musk personally. His willingness to take engineering risks has clearly driven real breakthroughs, this motor being one example. But his public statements and controversies have, at various points, created friction with parts of Tesla's customer base and investor community. For a lot of buyers, trust in a company and its leadership carries as much weight as any spec sheet, and that's a variable no amount of clever rotor engineering can fully offset. Stepping back, what makes this story worth paying attention to isn't really the 0 to 60 number, impressive as it is. It's what the process reveals about how meaningful advances actually happen in a mature industry like automotive manufacturing. Nobody invented a new law of physics here. Carbon fiber's strength and stiffness properties have been understood and used in aerospace for decades. What Tesla did was take a known material solution to a well-understood problem, centrifugal stress on a spinning rotor, and figure out how to manufacture it reliably enough to put it in a car that customers could actually buy and drive every day. That's a less dramatic story than Tesla invents a revolutionary new motor, but it's arguably a more useful one, because it's the kind of incremental, execution-focused progress that tends to actually stick around, long after the headlines fade. Whether this specific technology eventually makes its way into cheaper vehicles, other industries like aviation or grid-scale energy storage, or gets matched by a competitor in the next few years is genuinely uncertain, and anyone who tells you they know for sure is guessing. What is clear is that the gap between announcing a good idea and manufacturing it at scale, reliably, thousands of times a day, is where most of the real competitive advantage in this industry actually lives. Tesla's carbon-wrapped rotor is a solid reminder of that. The blueprint was never really the hard part. The factory floor was. There's one more layer to the story that's worth sitting with, and it has to do with how modern manufacturing actually works underneath the marketing. Tesla doesn't build every part of every motor from scratch for every trim level. Engineers who've examined the Plaid's motor closely have pointed out that the copper stator winding architecture inside the high-performance version shares its fundamental design with far more ordinary, single-motor versions of Tesla's lineup. That's not a scandal or a shortcut. It's smart industrial design. Building an entirely new winding architecture from the ground up requires enormous tooling investment, so instead, Tesla takes a proven, cost-efficient core design and adds the exotic reinforcement, in this case the carbon sleeve, only where the extreme performance demands actually require it. Think of it the way a tailor uses the same reliable thread for a formal suit and a work jacket, and reserves the premium materials for the parts of the garment that need to withstand the most stress. That kind of platform sharing is exactly how large-scale manufacturers keep costs manageable while still pushing performance at the top of a lineup. It's also worth understanding just how tight the manufacturing tolerances are here, because the numbers put the difficulty into perspective. Engineers involved in this kind of high-tension fiber winding work in increments measured in micrometers, distances smaller than the width of a human hair. Even a slight inconsistency in tension across the wrap can create a rotor that's imbalanced enough to cause vibration or premature, where once it's spinning at tens of thousands of revolutions per minute. That's the kind of tolerance usually associated with aerospace components, not consumer vehicles rolling off an assembly line by the thousands every week. Getting that consistency at high volume, without a defect rate that would sink the economics of the whole product, is a genuinely underappreciated manufacturing accomplishment, separate from whatever you think about the marketing language wrapped around it. It's also fair to ask what this means for the average person who isn't shopping for a plaid trim performance sedan. Right now, the honest answer is, not much, directly. This specific rotor technology lives in Tesla's most expensive performance vehicles, not in the more affordable trims that make up the bulk of the company's sales volume. But manufacturing innovations in the auto industry have a long history of trickling downward once the tooling costs are paid off and the production process matures. The touchscreen interface and over-the-air software updates that once felt like luxury novelties in the original Model S are now standard expectations across nearly every new vehicle segment, electric or not. Whether the carbon-wrapped rotor follows that same trajectory into mainstream trims, or stays a performance-tier feature indefinitely, will depend less on the engineering and more on the economics of scaling the winding process down to a price point that makes sense for a mass-market car. There's also a competitive dimension worth watching closely over the next few years, whether rival automakers attempt to license, replicate, or independently develop a comparable carbon-wrap rotor approach of their own. So far, most competitors have focused their engineering resources elsewhere, on battery chemistry, charging speed, or software, rather than chasing this specific rotor architecture. That could change quickly if a rival concludes the performance gains are worth the manufacturing investment, but building the specialized winding equipment and quality control process from nothing, the same challenge Tesla itself faced starting from zero, is not a quick or cheap undertaking for anyone entering that race late. At the end of the day, this story isn't really about one car going fast. It's a useful case study in how genuine competitive advantage gets built in a hardware business, not through a single secret ingredient, but through the unglamorous, expensive, and easy-to-overlook work of turning a sound engineering idea into something that can be built correctly, over and over, at a price that makes sense. That's a much less cinematic story than revolutionary new motor changes everything, but it's the one that actually explains why this particular piece of engineering has been difficult for anyone else to match so far.